Hello. So here I am. I'm in my home directory on the Pitzer cluster. I just connect to it via a web browser using ondemand.osc.edu. I just finished recording a screencast in which I quickly went through using all the scripts to automate equilibrating our system for sample free energy calculation. Now, in this screencast, I'm going to go through the same process, but I'm going to spend more time in trying to describe better what's happening in all the files. Okay. Again, my hope is that in your future research, if you want to perform a solvation free energy calculation, more than likely you'll need to come up with some new force fields for your system of interest, and so there's plenty of great free tools to do that. But then you can take the scripts and files that I'm sharing with you and modify those, update those for your case of interest. And so by going through them, hopefully everything will make sense and you'll be able to adapt those in the future. So from our home directory, okay, I'm going to start by navigating to our group space. So that's cd/fs, ESS, then we are PMIU 0186. Okay. And in the last screencast, right, so again, this is our, this directory contains the force fields for our sample calculation. We're going to calculate the hydration free energy of a drug in tip 4P water. Sample calculation 33 contains a setup for our sample calculation. And what I did in the last screencast is I copied the sample calculation, made a new directory with my name on it, and that's what I quickly went through. Okay, and that job is currently running to equilibrate our systems. And so I want to do it again, but I'm going to spend more time doing so. So I'm going to start by again copying sample calculation 33, and let me call this MIU 0105, and maybe I add a long on there since this is the long-winded version of how to get it submitted. Okay, but again, use your username. That way, if you need help, I can go in there. I can help you troubleshoot and debug. Okay, and now I'm going to open up the directory. Okay, so if I type ls, okay, now what we have going on in here is the first step before I can perform my free energy calculation is I need to equilibrate my system. We're going to equilibrate our system in our target state in which our solutes fully interacting. Okay. Once we have that equilibrated state, when we perform our free energy calculation, in our case, we'll essentially have 15 independent simulations that differ in the lambda value, so the scaling of the LJ in electrostatic interactions. So we'll use in all of those, right, our starting structure will be this final equilibrated structure. And what we'll do is we'll run a longer trajectory. So I believe it's 17.5 nanoseconds I have it set up for. And what we'll do is when we perform the analysis, we'll throw out, say, the first 2.5 nanoseconds. We'll take those as additional equilibration at that given lambda. Okay, but rather than doing 15 separate equilibration phases, I'm going to set up one structure in our target state, and that's going to become our starting point for each lambda. Now, when we equilibrate our system, okay, we're going to do this so I've got 4 folders that are essentially going to get us to that point. Okay. The first thing that we're going to do is we need to come up with an initial structure, and to do that, I like to use PacMol. Okay, so PacMol will randomly insert our molecules in a box. Then what we'll do is once we have our initial structure, we'll then perform a basic minimization using Gromacs. When we perform our minimization, the goal is not to perform a true minimization. The purpose is just if PacMol created any bad contacts, I want to remove those before I begin to perform my MD simulations. Right? Because if I have a bad contact, that could result in a huge spike in energy and force, which would cause my trajectory to become unstable and cause Gromacs to crash. All right, so minimization is just a few thousand steps of steepest descent minimization to remove any bad contacts that may have been created or bad configurations that may have been created. Then in equilibration, we'll take it in 2 stages. In the first stage, we're going to equilibrate with the Berenstain thermostat and barostat. Remember, my Berenstain thermostat and barostat do not sample the correct NPT ensemble. However, they're very stable, right? They suppress the fluctuations of my system. So for our starting structure, or just coming off of minimization, where we're not certain how good of a structure we have, we're going to start with our Berenson thermostat and barostat, and then in step 2, we'll equilibrate with the correct thermostat and barostat. In this case, we'll use stochastic velocity rescaling, thermostat, and Pernilla-Raman barostat. Then that'll get us to our starting structure, which we need to perform our free energy calculations. And so again, I've tried to automate this as much as possible. So I'm going to start by opening up initial config. Okay, and so in here I'm going to see 2 files. Okay, the .in file is a PacMol input file, and you can see the PacMol website for details on all sorts of cool tricks and things, different types of systems they can set up. And then this script is going to be the script that's going to run PacMol and do all the necessary conversions, and we'll look at that in a second. Okay, but if I start by looking at the PacMol file, okay, I'm going to use Vim. We'll go over to the file editor and how you can view things and edit things when we need to edit things. But for now, I'm going to use Vim in the interest of time. And so the way PacMol works is, again, basically the picture to have in your head is we're going to tell PacMol, this is the size box I want. This is how many molecules of each species I want to pack in that box. Okay. So the first parameter is the tolerance. My fuzzy memory is that the tolerance of 2 is going to specify that I have a minimum of 2 angstroms before atoms in my system. Max iterations, I believe, is the maximum number of iterations that will be attempted to place each molecule. You give it a random seed. And then file type, we're going to work with XYZ. Output, so this is going to be the name of the final box that I pack. Okay, so now for the main important interesting parts. So first I'm going to put my solute molecule in the box, and then I'm going to put my solvent. Okay, so the order, I could switch it, but it's important that you keep track of it, because what will happen is when we ultimately get to our free energy calculation, okay, we're going to need to tell Gromacs which molecule is our solute. Okay, so I always like to keep it at the top of the box. Okay, so if I had, say, 10 solutes, so maybe 10 of these drug molecules, I'm at a finite concentration. I always, that first one's going to be the one I'm going to change and mess with. Okay, and then this will have to match up with our topology files. So the first line structures. Okay, so you need to provide Gromacs or PacMol with an XYZ structure of the molecule, of the coordinates of your molecule. Okay, so I have that located in our group space. Okay, and then next is how many molecules do you want? So you want to pack 1. And then we need to define our box. So we're going to say it's a cube. So origin's at 0, 0, 0, and it has an edge length of 45 angstroms. We do the same thing with our solvent, in this case water. You point to the XYZ. Okay, and I'll make a note. I just realized that I need to update to the path for this workshop, not my weekly workshop that I'm putting on right now, but that's not going to change. So I point to water. We have 3,000 waters. Again, cubic box at the origin, box length of 45 angstroms. Okay. So now looking at initial config.sh in terms of going through things. Okay, first thing I'm going to do here is I'm going to load Gromacs. It's going to be necessary for when I convert my final structure to a Gromacs.gro, so Gromacs format. And the first thing I'm going to do is I'm going to call PacMol, and I'm going to pass PacMol my input file, and so it'll take that input file and pack a box according to my specifications. And then in the next step, so PacMol created an XYZ file. When I get to Gromacs and edit conf to create a Gromacs format file, a .gro file, I need to get a PDB. When I've tried to pack PDBs before in PacMol, I've always gotten errors. So the solution I have found is I pack an XYZ, and then once I have my XYZ structure, I then use OpenBabel to convert my XYZ to PDB. Okay, so again, if you read the PacMol documentation, you should be able to pack a PDB or get a packed box in a PDB file format. But whenever I do it, I always get errors. And so I instead pack an XYZ, and then once I have my XYZ structure, I'll convert the XYZ to PDB using Babel. Okay. Now, once I have the PDB file from Babel, I can then use edit conf in Gromacs. And so here I'm telling Gromacs, okay, I'm going to run edit conf, and my input's going to be my PDB of my packed box from Open Babel. My output is going to be a file with the same name, but it's going to be an extension .grow. So that's a Gromacs file format. And it's going to be a cubic box. So box type is cubic. Now for the edge lengths here, okay, this is very important. All right, this is going to be the same dimensions as the box that I packed in Packmol. Okay, so this needs to be the same dimensions as the box I packed in Packmol. Okay, cool. And so then the result of this will be a cubic box in Gromacs format that's identical to that box that Packmol packed. So what we need to do next is subtle, but it's incredibly important. Okay, and so if you don't do the next step and you get an error when you perform your minimization, if it crashes and burns, it's probably because you missed this next step. And so basically, when I run Packmol, Packmol has no concept of periodic boundary conditions. It's just I define a cubic box of edge length 45 angstroms, and I put all my molecules in there. Okay, it doesn't try and account for periodic boundary conditions. We need to account for periodic boundary conditions, or attempt to, before we run our minimization and then MD simulation. Okay, and so when we looked at the Packmol input file, we had a tolerance of 2. All right, and my understanding or my recollection is that should be that there should be at least 2 angstroms between each atom intermolecule. All right, so what I'm going to do now is if I have a cubic box of 45 angstroms and I haven't accounted for periodic boundary conditions, is in the sed command, right? Essentially, I'm going to go into my grow file and I'm looking for the line in which I define the dimensions of my box. Okay, here they're 45 angstroms or 4.5 nanometers. It's the last line in the grow file. And what I'm going to do is I'm going to change 4.5 nanometers to 45 angstroms to 4.6 nanometers or 45 angstroms. Okay, I'm going to add essentially an angstrom of vacuum around my cube. Okay, so that when I replicate that in its periodic image, which also has then this buffer of 1 angstrom around it, I should have at least 2 angstroms between any molecules in their nearest image. Okay, so this is important because otherwise what could happen is you could get a molecule really close to the edge when you pack that box using Packmol, and when you apply periodic boundary conditions, in its periodic image, there might be another molecule really close to the edge, which leads to really bad contact and your simulation crashing and burning. Okay, so what I'm doing here with the sed is I'm manually going into my grow file, changing the box size to be 1 angstrom larger, so half my tolerance. Okay, so basically I'm packing this box, I'm converting it to grow, and then what I'm doing is I'm going in and editing the grow file and making my box, my edge length 1 angstrom larger while keeping the position of all my molecules the same. Okay. As a side note, many years ago, maybe just a year or 2 ago, instead of doing this sed, I used to always just go to edit conf, and the thought I had in my head is I could just change the box size here from 4.5 nanometers to 4.6. But typically that doesn't work. What ends up happening, or my understanding is, Gromacs is scaling the coordinates of all your molecules to that new box size. Okay, so that you don't want to do. What you want to do is go in and manually change the size of the box. Okay. All right, so what I'm going to do is I'm going to exit out of here, and to set up my system, I'm just going to do period / initial config.sh. Okay, and so Packmol will start, it'll pack its box. So if you find this has taken a really long time, it may be that for your system you might need to increase the box or maybe play around with the tolerance. Okay, and so when I try and estimate the box size, typically I would go to say get an experimental density, and for a given number of molecules try and estimate what the box size is, or usually go in reverse. If I want a box of this dimension, this edge length, how many molecules do I need? And so usually I base that off of experiment. So If you find it's taking a long time, you might kill it and mess around with your box dimensions. All right, one note I'll point out because it'll come up again later is Babel complains a little bit about my atom names. And so what this is just, so if I were to go to my PacMol input file, okay, so just to look at my XYZ for water, the issue is just the names I use. So I'm just going to highlight that and it copies it. Okay, so I'm a Vim. Okay, just click the middle wheel and paste. And actually I wanted water. All right, yeah. Oh, I copied the wrong molecule. So, see, this is live. Okay, so I want to look at water. Water is the interesting one that I was complaining about. Okay, so highlight it and Vim it. Okay, so this is just an XYZ structure of my molecule. And when I defined my, labeled my atoms here, I use OW to correspond to water, oxygen, HW, water, hydrogen, and MW is the imaginary site. So these are the names I used in my force field file to try and distinguish between atom types. So Babel is just saying, hey, I'm converting the structure, and I have these these atom types that aren't found on the periodic table. What's going on? Don't worry about it for now. All is good. Ultimately, when we go to set up our first minimization run, everything will be corrected, and Gromacs will make sure that the names used are consistent with our force field files. Okay. But if it bothers you, you could go in and change the water file. Now, what I'm mainly looking for here is sample 733 input.grow. Okay, that's going to be the starting structure that I'm going to use. Okay, that I'm going to build off of. Okay, cool. So from here, after I have my minimization complete, or initial config generated, I'm going to go perform my minimization. So I'm going to back up a directory, cd dot dot. I'm going to refresh and look at everything, and I'm going to open up minimization. Okay, so type ls, and so within minimization, I have 4 files. Okay, I'm going to have the setup script, which will take that in a second, which will set up and automate everything. Submit job is going to be our job submission script that we'll send to the scheduler. Okay, but the new 2 files that we'll have here are going to be ff.top, our topology file used by Gromacs, and input.mdp. Right, it's going to tell Gromacs how to perform the calculations. So if I look at the topology file, okay, so our force field files, I have them all located in our group space, and so you'll probably need to change your come up with new ITP files for whatever systems it is you're interested in or looking at. Okay, but key is when I packed my box, solute was molecule number 1, then came solvent. Okay, and so when I generate my system, right, that order is going to be the same here. First comes my solute, and then comes my solvent. Okay, that's my Gromacs topology file. You will definitely need to update that for different system in the future, but it very well may be that's the only file you need to update, along with the XYZ structures for your molecules and ITP files for them. Then the other one we'll look at is the MDP file. So note when we perform our minimization here, we don't care if we find some true global minimum or even local minimum if we really minimize our system. The purpose of this is PacMol is just based on our XYZ structures that we give it, randomly sticking molecules in a box. So all we're trying to do here is check to make sure PacMol hasn't created any really bad configurations. Right? If there's any really bad configurations in our system, we want to eliminate them. So you can think of this as a very basic relaxation. Okay, so our MDP file, right, contains everything that you would have in a normal MDP file for a minimization run. Okay, and so I'm going to look at actually let me look at submit job first. Okay, because then setup you'll see what needs to be changed. So when we perform our minimization, okay, so the minimization we could perform interactively on the desktop on one processor, but sometimes it's not the best, especially for larger systems. So we're going to send this job to run on a remote node. Okay, so this is going to be a submission script to that we're submitting to the scheduler to submit our job or run our job on a remote node. Okay, so the top part contains information for the scheduler. Okay, so we've got this set up to use a bash script. Okay, then the first line here, this hashtag sbatch. Okay, I give it a job name, so I'm calling it sample733 underscore water. So this name will appear if I want to check on the status of my job. This will appear in emails that I receive from OSC about my jobs. So give it something so that if you want to check on the status of your job, you know exactly what job you have, right? Imagine you've got 30 jobs running and you want to be able to differentiate. The second line, okay, so in our setup script, we're going to update this, okay, so you know what we're updating, is this is going to be the email address that the supercomputer uses to communicate to you. Okay, and so looking ahead to the next line, I tell it to send. This is telling it to send us an email when the job ends. So it'll send us an email if the job gets killed, because there's an error, if the computer crashes, or just if the job finishes as normal. Okay, and then the line above it is the email address it's going to use. Right, put your email address in there. If you want more emails than just when it ends, you can look at the Slurm documentation on OSC's website, and you can get notifications when your job begins and other such notifications. All right, the next line is the resources we're requesting. So we're going to request one node, and we're just going to request 10 of the processors on that node. So we have 3,000 waters, but our molecule or system really isn't all that large. And so we're not going to scale too big here. We're limited by domain decomposition and just not necessary. These are going to be pretty fast calculations. They're going to be very fast calculations. Okay, so this will be the number of resources that we'll want. You can play around with increasing that or decreasing it if you want. And then we need to choose our wall time on the next line. So wall time, so in general, so if you have an estimate of how long your job will take, that's great. Even if I have an estimate, I always like to overshoot it, because what will happen is if I make a really big wall clock request, okay, so what will happen is if my wall time request is too big, I'm going to sit in the queue longer because it might take longer for OSC to be able to schedule my job to run. What I don't want is to underestimate it, because what happens is if I submit a job and I request, say, 1 hour, and it's not done at 1 hour, the supercomputer is going to kill it. Okay, doesn't matter if it finished or not, it's going to kill it because I only requested 1 hour. So, ideally, if you have a good estimate, you want to set something close to it, but I would say always overshoot to prevent your job from getting killed. I'd rather wait in the queue a little longer than have it get killed prematurely. I can tell you I've never waited in the queue, that long, right? Even if it's a day, it's better than the job getting killed after some period of time, having to go in, fix it up, and resubmit it and wait in line again. All right, now the last line is really important. OSC has projects. You could think of them as accounts that ultimately get billed for work. So for our workshop, OSC's given us an allocation, and our allocation, our group is PMIU 0186. So this just tells OSC who to build. So within the biophysics school, use 186. If you're in my weekly workshop, we use 185 for that. Okay. All right, then from there, okay, first thing we're going to do is we're going to load Gromacs. And so this is 2020.2 is the default version of Gromacs installed. And then here, this variable keyword, we're going to open up the directory that the job was submitted from. All right, so now a little explanation before we move on. Okay, in a second, we'll go back. I'll show you setup script, and we'll set up our minimization run. So Gromacs has some pre-processing that'll run. So as long as that works, you're good to go to run your calculation. Okay, so the first thing we're going to do here is that GMXD, we're running in the double precision version of Gromacs installed. We're going to run, okay, our minimization run. Okay, so NT tells it how many threads to use, right? And we're requesting 10 nodes, so that's going to be 10. So this variable will give me this number. If I want to change it up there, I don't need to change it down here. And then the default name of our output or of our inputs and outputs are going to be this sample 733 min being me telling minimization. All right, when I run the minimization, okay, it's going to be relatively short. It's going to take a minute or two. But what I don't want to do is submit a job for the minimization, have it finish, then I have to go back in, set up my equilibration, run it, potentially wait in queue again, wait for that to finish, and then do the same thing again for the second. So I just have it set up so it'll take care of everything at once. So this will run my minimization. Then once my minimization's done, I'm going to require or copy the topology file, the force field file, to my first equilibration folder, along with my final structure. Okay, bam, I'm going to copy that over to equilibration, and I'm going to rename it instead of min.grow, which would be our final structure for the minimization. It's going to be my initial structure in my NPT equilibration, so I call it input.grow. I'll navigate to my equilibration 1 folder, run my Gromacs preprocessing, run the trajectory, run the simulation. And then I repeat to run my second equilibration. And so basically, I'm going to run all three of these equilibration steps sequentially with one script, so I don't need to go in, resubmit any jobs, or resubmit or reset anything up. Okay, so this will take care of everything, and once this is done, I've got my structure that I can then take and perform or use to perform my free energy calculations. All right. So next, okay, I'm going to look at setup.sh. This is my submission script. Okay, and I'll show you in the editor how you can view files again and edit this one. So if I go through, it's a bash script. Okay, so again, I execute this. It's as if I did everything in my command line. And so the first thing I'm going to do is, in order to perform my minimization, I need my starting structure. So I'm going to copy that from my initial config directory. Okay, I'm going to make sure I have Gromacs loaded again. Okay, even if it's already loaded, if I try and load it again, no problem. And then Gromp is Gromacs' pre-processing. Okay, so reading through this, right? So I need my input.mdp file, and so I always use this input kind of string to designate input files to Gromacs. And then when I run my Gromp to get the process files, and when I get, say, my final trajectory, I'm always going to add on, in this case, the extension min. When I run my equilibrations, I'll use npt just to kind of differentiate what they are. So when I run Gromp, okay, so Gromp's going to need three things. Okay, it's going to need to have an input.mdp file that contains my simulation protocol for Gromacs. It's going to need input.grow. Okay, it's going to need a grow file, which is my initial starting structure. And then it needs a force field file, right? So you need to tell it how everything's interacting. Okay, so it needs my topology file, my grow file, and my MDP file. Okay, so I have these labels as input. Okay, my starting, the parameters for this simulation plus the starting structure, and then my force field file. And what's going to come out, okay, is going to be a TPR file, which we'll use. This is what's actually going to be used to run our simulation, and an MDP file, which has all the other default parameters, which we didn't specify, filled in. All right, and as long as that runs without any errors, you are going to be good to go, right? You can be rest assured things are going to run correctly. Now, the one thing you will need to edit is when we looked at submit-job.sh, our job submission script, is you need to change your email, right? Don't use my email. I don't want to receive a notice that your job ended. You want to receive that notice, okay? And so sed is will replace occurrences of my email address, which with whatever you list here, right? So right now it's you@you.com. This you want to update to be your email address. So you can edit it in Vim, right? So again, if I go type I can get into insert mode, and I can delete and edit. Okay, but I'm gonna quit without saving. Okay. The other way, which you might prefer, okay, is I'm gonna go in Files. I'm gonna navigate to our group space again to kind of go through this whole process. Okay, because we haven't gone in here yet. I go into this long folder, minimization. What I'm trying to edit is setup.sh. So I can click on the drop down, click edit, and I can edit. So you want to take u@u.com and you want to replace that with your email address. Okay. In my case, it's the same, but it'll work just fine. So I save it, right? So now it's saved. It won't let me save it again. And I can close. And just to confirm over here, if I vim setup, right, it's been changed. All right, so that's it. So I'm going to do a period / setup.sh. Okay, it'll run Gromacs's pre-processing. Okay, so it gave me one warning. It hasn't given me an error. It gave me one warning. And basically it just comes down to this atom mismatches again. Okay, again, don't worry about it. Right, you'll see everything is perfectly fine, and that final trajectory from our minimization, all the atom types are going to be labeled correctly. Okay. So all right, so minimization is set up. Then to run it, okay, the command is sbatch submit job.sh. Sbatch is submitting our job submission script to the scheduler. Okay, so if I check on my status, qstat-u and my username. Okay, so the first one I have listed with the same name is from the last screencast I recorded, the quick version of me going through everything. And then the second one is the one I just submitted, which is in Q. Right, so I probably should have changed the job title, but all's good. Okay, cool. Okay, so this will take some time. Okay, but then I'm going to open up NPT Equilibration 1. Okay, the only file that's in here is the input.mdp file, right? The simulation parameters we're going to use for that equilibration with the Berenson thermostat and barostat. What will happen is I'll just copy the force field file from minimization, because that's not going to change, and I'll copy the final structure from the minimization, and that'll become my initial structure here. Right? I like to propagate the force field file because I edit it once in minimization, and that's the only place I need to change it. So, if I, look at a different system, I'll need to come up with new XYZ structures for PACMOL. I'll need new ITP files, new force field files, but then I come up with that new, topology file, ff.top file in minimization, and that's the only place I need to change it. I'll just keep propagating it. If I were to vim this input file, right, it's going to look, differently. So it's a basic NPT simulation, 1 nanosecond, where I use Berenson thermostat and barostat. Okay, so we have standard simulation protocol, and then Berenson thermostat and barostat. And then if I go to equilibration 2, okay, similar. The only thing there is an input.mdp file. The force field file gets copied from equilibration 1. The final structure from equilibration 1 gets copied here as well. Okay, and now it's going to be a standard NPT run, where I'm running or using velocity rescale in Pernilla-Raman barostat. Okay, but that's it. Okay, and just to give you a preview, so once you get your email that your equilibration run's all done, then you can go in and set up and run your free energy calculation. Okay, so this one it's not in that minimization script, and the reason being is we're going to now run. So we were running one, equilibrating one system before, and now we're going to replicate that, and we're going to run 15 independent simulations, one at each different value of my scaling of my LJ and electrostatic interactions. Okay, so if I go to open up FECalc, okay, you're going to see 15 of these input.mdp files. Okay, they go from 0 to 14, 0 being my reference state in which my intermolecular interactions between the solute and solvent are turned off, and 14 is fully interacting. Okay, so there's just 14 copies of these. And if I open up, let's start with 0. Okay, the top is going to look pretty similar. Okay, I have this set up so that we'll run 17.5 nanosecond trajectories. And what we'll do is we'll throw out the first 2.5. So we'll equilibrate that one structure in which our solute's fully interacting with the solvent. Okay, we'll equilibrate in our target ensemble. And then rather than having, a bunch of different independent equilibrations, 15 of them, we'll just have that one target system. Then when we run our free energy calculations, we'll throw on some extra time that we'll discard and take to be, equilibration within that specific lambda, right? Equilibration relative to that target state. Okay, in terms of which state to choose, I use the target because if I think about the reference could have molecules overlapping and things like that. So I don't want to equilibrate there because that's not going to work for most all of the other states. So everything's pretty much the same. There's a note here that I've changed the frequency compared to the equilibrations of how frequently I write the energies, and I just wrote this so it coincides with how frequent I'm performing these fictitious perturbations and writing the disk. Okay. And then the big difference, as you'll see, is, and actually I should go up to the top. Okay, remember we need to use a local thermostat, and so we use the stochastic dynamics integrator in MATLAB. Okay, so it's important that we use a stochastic thermostat because when my solute's not coupled or only weakly coupled, we need to make sure that we're adequately able to control its temperature. And then the free energy stuff, right, the new section comes at the bottom, right? We have this free energy control in which we tell Gromacs we're going to perform a free energy calculation. All right, we're going to calculate these fictitious perturbations. We set our soft core potential parameters. Okay, we tell Gromacs that the molecule that we're going to couple or decouple is this sample molecule, sample type. And so if you go back to our topology file, right, we call our solute is type sample. Okay, so that's it. Now let's say, for example, you had 10 sample molecules. You only want to couple or decouple one of them. So you would say rename the atom type of one of those. You would call it something different and point to that molecule here. Then this tells us what state we're going to start in. Okay, and so kind of moving ahead. Okay, here we list out the scaling used in states 0 up to 14. Okay, so I have my M value. That's a comment line, but helping set it up in a table so I match things out. State 0, my lambda value for LJ in electrostatics is bold 0. It's decoupled. And then I first turn on LJ, keeping electrostatic off. And then I turn on electrostatics, keeping LJ full. So this init lambda state tells me what state I'm in. I need to give Gromacs all of the other states, so when I perform my fictitious perturbations, I'm calculating the perturbation between the state I'm in and all other states. Also important is, so again, my 0 state is non-interacting. My fully interacting state, state 14, corresponds to full van der Waals and electrostatic interactions. And then we're going to make sure we don't mess with the intramolecular interactions. So remember, in general, atoms separated by 3 or more bonds, right? 4 or more bonds are going to be fully interacting. 3 or more, they're typically scaled. But for those atoms separated by 4 or more bonds, we want to make sure we don't touch those, right? Because we don't want to mess with the intramolecular interactions of our system. And yeah, that's that. So if I look at, say, 7, just for comparison, okay, what's going to change is, the Senate lambda state is 7, right? I'm in subensemble 7 for this case. A couple of things I changed too. Oh, I can't just scroll up. I've got to move up with my cursor. Is when I generate my system, I'll use a different random seed for each case. Right, they're all starting from that same initial structure, corresponding to our fully interacting system. So I'll regenerate the velocities for each case, and I'll give each one a different random seed. Okay, just being anal to, as I set things up, changing that seed so I get some unique trajectory, which will already be unique because I have a different scale factor. Okay, so there's just 15 of those MDP files now. The scripts, right? So we're running a bunch of independent simulations. So I have 15 scripts. Okay, each script is going to look very much the same, right? Just running a specific case. And so rather than typing sbatch 15 times, if I vim FE submit, all right, I've got a script in which I just do that for you, copying and pasting. So all you'll need to do here is you'll need, once your equilibration is done, so once you get the email that it's done and it's finished correctly, exit status 0, I'll go into FE setup. Okay, so when I run this, it's going to copy my topology file from my equilibration run. I'll copy the final configuration from my equilibration run and rename it input.grow, load Gromacs, run gromp 15 times, one for each case. And then what you need to go in and edit is update your email address again, right? Don't send emails to me, send them to yourself. Use sed here because you've got to update all 15 scripts, right? And so this will get it in one command, changing my email to yours. So all you'll do when your simulation's done is you'll run, so go into FE setup, update your email address, then do /FE setup. Then once that works successfully, /FE submit will submit all 15 jobs. And we'll go through that once my equilibration's done and I can demonstrate how to exactly do that. Okay, so I hope that helps. Can't wait to see you in the workshop, right? And you can always ask me more questions.